What if I told you that aiming for 100% test coverage is actually making your software more brittle?
Yeah, or that configuring your continuous integration pipeline to fail fast is, actively sabotaging your debugging speed.
Right. It sounds totally backward. I mean, we spend so much time optimizing our local environments, but when you zoom out to managing a really massive code base, all that conventional wisdom just it starts to break down.
It completely fractures, honestly,
Yeah.
because the tactics that keep a single repository stable will absolutely choke a multi-repo ecosystem.
Oh, for sure.
At a certain scale, you're not just writing code anymore. You are basically managing a living, breathing, distributed system of dependencies.
Exactly. And that is exactly what we're looking at today. We are doing a deep dive into a literal masterclass on development scale.
Hmm.
It's a wildly insightful 2026 presentation by the developer Luxira36, and it's called Advanced Git and Multi-Repo CI Orchestration.
Right, which is the highly anticipated sequel to their open source DevFlow presentation.
Yes. And our mission for this deep dive is to basically extract the absolute core insights from Lux 036 to help you, the listener, scale your own workflow.
Because orchestrating 20 repositories at the exact same time without causing like a total systemic collapse is no joke.
No, it's an incredible feat. So, okay, let's unpack this because, you really can't orchestrate 20 repositories in the cloud until your local repository management is structurally sound.
You really can't. You have to start at the foundation.
Right. And the presentation starts by revisiting that classic, eternal debate, Git merge versus Git rebase.
Ugh, the religious war of developers everywhere.
Right. But the way this presentation frames the underlying mechanics is just, it's really helpful.
It is because it strips away all that typical developer dogma and just focuses purely on graph topology.
Mm-hmm.
Like they characterize Git merge as the historian.
I love that term.
Right. Because a merge preserves the complete unaltered timeline of your work. It leaves these definitive nodes in your graph that show exactly where a branch diverged and, where it reconnected.
So I took like 5 really messy experimental steps to finally arrive at a solution.
The historian permanently records all 5 of those messy steps. It's structural honesty, which is what makes it fundamentally safe for shared branches.
Got it. And then on the other side, we have Git rebase, which they characterize as the storyteller.
Exactly.
Because with a rebase, you get this beautifully clean, linear commit history, which, I mean, it makes tracing bugs with a binary search incredibly straightforward.
Oh, it's so much easier to read.
But the massive trade-off is that you are literally rewriting history.
Yes, you are.
You're like unplugging your local commits, fast forwarding the base pointer, and then reclucking those commits back in.
Mm-hmm.
And Git is generating entirely new cryptographic SHA-1 hashes for every single one of those commits.
Which is exactly why the source establishes this absolute non-negotiable golden rule. You never, ever rebase commits that have been pushed to a shared branch.
Never. To put that in perspective for you listening, pushing a rebase to a shared branch is basically like, okay, imagine you're rewriting the chapters of a published history book while your co-authors are literally in the middle of referencing it.
Oh, that's a perfect analogy.
Right. Like one author is writing a paragraph based on chapter 4, but you've just secretly deleted chapter 4, combined it with chapter 3, and changed all the page numbers.
Chaos.
Total, unmitigated chaos ensues. Nobody's local repositories sync up with the remote anymore. Git will actively block your collaborators from pushing their work.
Because the fallout is severe. You have orphaned the commit graph that your entire team is relying on.
Right. So to resolve this tension, because obviously we want a clean story, but we need an accurate history.
Yes.
The presentation details a really specific hybrid workflow.
Yeah, and it's brilliant. The methodology is basically you rebase locally, but you merge at the boundary. So when you're developing a feature locally, you rebase against the main branch. You squash all those messy work in progress commits into logical units.
So your local story is perfectly linear.
Exactly.
But wait, doing a merge at the very end creates an extra commit, right? Doesn't that just clutter up the history we literally just spent time cleaning up with the rebase?
Well, it creates a specific type of commit because you use git merge -- no fast forward flag.
Ah, okay.
Even if Git detects that it could just, easily slide your commits into the main branch in a straight line, that flag forces it to create a dedicated merge node.
Okay, so you are explicitly marking the boundary of that feature integration.
Exactly. You get the clean, readable narrative of a rebase inside the feature work, but it's bounded by the safe historical marker of a merge on the main branch.
That is so smart. And to guarantee that local narrative is perfectly aligned before you even try to merge, the source details this great quantitative method. They call it the zero commit gap trick.
Oh yeah, using the get revlist command.
Right, get revlist dash dash count. Because, I mean, instead of guessing or trying to visually parse some massive graph in your terminal, which is terrible,
Oh, it's impossible.
Revlist mathematically compares the nodes between your local branch and the remote tracking branch. And if
Uh,
that command returns a zero,
you know definitively that your local state is a perfect fast forward candidate. You have mathematically eliminated the possibility of a divergence.
which is awesome. But, okay, keeping a single local repository mathematically clean is a great foundation.
Mhm.
But the moment you try to apply that pristine logic to 20 repositories at once, you hit a completely new bottleneck.
A massive bottleneck.
Right. You can't just sequentially change directories in your terminal and manually type git commands for every single repo. You would lose hours.
You'd be there all day. Which brings us to the bulk operations they detailed in the live session of the presentation.
Yes, utilizing the GitHub command line interface. And the statistics from this session are just wild to
Those
me.
are staggering.
The presenter successfully fast forwarded 15 repositories to main and 5 to master. And then, executing bulk API calls, they created 20 releases in about 60 seconds.
Yeah.
7 entirely new releases and 13 version bumps in 60 seconds.
Right. And executing that volume of state changes across a distributed architecture in a minute requires completely bypassing your local Git mechanisms.
Right.
They aren't pulling, merging, and pushing 20 times. They're utilizing that GCLI to instruct the GitHub backend to perform the fast forwards directly on the remote servers.
Bypassing the local machine entirely.
Exactly. It eliminates network latency, local file locks, and all that context switching.
But, okay, here's where it gets really interesting to me, but also, frankly, slightly terrifying.
Yeah.
Moving that fast, bypassing all those local checks, and triggering 20 concurrent release pipelines. How do you not just hit massive API rate limits or like trigger a total chain reaction of broken upstream dependencies?
Well, what's fascinating here is that velocity is purely a byproduct of visibility. Right. You can only safely execute back-end bulk operations if you have a control tower monitoring the file out in real time. The GACLI isn't just used for state changes. They use it as a multi-repo diagnostic dashboard. So commands like grun and grunview, they allow a developer to query the pipeline status of all 20 repositories simultaneously, right from the terminal.
So you're basically aggregating the metadata of every single CI runner.
Exactly. Rather than manually clicking through dozens of web browser tabs to hunt down a failed step in some massive log file, you pipe the runner telemetry directly into your local standard output.
Wow.
The presenter actually demonstrates going from identifying a failure to pinpointing the exact line of code that triggered it in under 30 seconds.
That is incredible.
Yeah.
But you can only trust an automated 60-second release if your safety net is actually designed to catch the bugs first.
Right.
Which leads us directly into the underlying architecture of that safety net. The presentation introduces what they call the matrix strategy for CI optimization. And there is a highly counterintuitive configuration discussed here. Explicitly setting fail fast to false in your testing matrix.
Which goes against everything most people are taught. The default behavior for most CI runners is to abort the entire matrix. The absolute millisecond one environment reports an error.
Because you want to save compute cycles, right?
Exactly. But when you are orchestrating complex multi-platform libraries, failing fast severely throttles your debugging speed.
Oh, how so?
Think about it. If you fix an error on Ubuntu, push the code, wait for the pipeline to spin up again, only to watch it immediately fail on Windows, you're just stuck in a synchronous bottleneck.
Oh, I see. So by setting fail fast to false, you are intentionally burning those extra compute cycles to map the entire failure surface area all at once.
Yes, you want every runner in the grid to finish its job so you can cross-reference the result.
Right, and the presentation gives a brilliant concrete example of this using a minimal matrix for publishing to PyPI. They test the oldest supported version, which is Python 3.9, alongside the latest features in 3.12 and 3.13, and then they cross-multiply that by running it on both Ubuntu and Windows.
And they explicitly note skipping macOS to save compute time unless you're actually hooking into macOS-specific system APIs.
Right, so the matrix effectively isolates your variables automatically. You aren't just getting a simple pass or fail. You're getting a highly specific diagnostic signature.
Mhm.
Let's make that signature concrete for you listening. So, say your matrix completes and Python 3.9 fails across all operating systems, but Python 3.11 passes.
Don't even need to read the stack trace.
Exactly. You instantly know you're likely dealing with a PP604 syntax issue because older Python interpreters just throw a syntax error when they hit that modern pipe syntax for union types.
Right. The matrix acts as a compiler check across time.
Yeah.
And conversely, if your Python versions all pass, but the Windows runner fails while the Linux runner succeeds, you immediately stop looking for syntax errors.
Right, it's environmental.
With really high probability that you have a path separator conflict. Or maybe a floating point precision difference in how the underlying C libraries handle math. The grid isolates the environmental variable for you.
That is so powerful. But to make a massive grid like that run efficiently enough to actually support a 60-second release cycle, the source emphasizes ruthless workflow hygiene.
Oh, absolutely ruthless.
Because if you're using like pip install git plus HTTPS directly from a remote repository, your runners are constantly pulling the bleeding edge of the default branch.
Which is a nightmare.
Right. Someone merges a breaking change on their end, and suddenly your perfectly fine code spontaneously fails its next run.
Because unpinned dependencies introduce massive non-determinism into the pipeline.
Mm-hmm.
The source mitigates this by rigidly declaring dependencies in a setup.cfg file for PyPI. That ensures the runners only pull stable version releases.
Okay.
And furthermore, they leverage Actions Cache to locally cache those dependency trees right on the GitHub runner.
And the presentation logs that caching those dependencies saves 30 to 60 seconds per CI run.
Which adds up.
Huge.
Yeah.
When you multiply 60 seconds by a 20 repository matrix executing, say, 10 times a day, you are reclaiming hours of raw compute time. And, more importantly, developer focus.
Yes. And you combine that caching with proactive environment upgrades like migrating from Node.js 20 to the default Node 24 in your actions, and you prevent technical debt from slowing down your runner provisioning.
Okay, so you've engineered this pipeline that isolates failures dimensionally and executes in seconds. It's beautiful.
It is.
But a high-velocity multi-repo release pipeline creates a really dangerous downstream effect. If you ship 20 releases in 60 seconds, your end users have absolutely no idea what just changed.
Not at all.
So what does this all mean for the poor developer who just wants to ship their code? I mean, if Git is already tracking every single commit, hash, author, and timestamp, why can't they just pipe the Git log output directly into the GitHub release notes and call it a day?
Well, the source makes a really sharp distinction here. A raw Git log is a record of engineering effort. But a change log must be a record of user value.
Ah, user value.
Right. Dumping 183 commits into a text box just creates severe information overload. The user has to mentally parse your internal refactoring tickets to figure out if their own integration is going to break.
Yeah, nobody has time for that. And the presentation explicitly lists writing vague descriptions, like just saying minor bug fixes or, silently dropping deprecation warnings as major anti-patterns.
Oh, they are the worst.
Why?
Nothing burns developer trust faster than updating a package, finding out a core class you rely on was deprecated, and seeing zero documentation about the migration path.
Right. So curation is mandatory.
Absolutely. The protocol they outline involves organizing the release by strict categories, features, fixes, and performance improvements.
Keep it organized.
You visibly credit external contributors, which is so important to sustain the open source ecosystem. You embed a deep link to the Git compare view so auditors can easily inspect the exact diffs if they want to. And above all else, breaking changes must be isolated and placed at the absolute top of the document. You are essentially translating the technical reality of the graph history into actionable intelligence for the consumer.
You're extracting the meaning from the noise. I love that.
Yeah.
So we have perfectly scaled releases, we have crystal clear change logs, and a light and fast CI matrices. But there is this psychological trap that developers often fall into when they manage to automate everything else so smoothly.
Oh, boy.
We have to talk about code coverage.
Yes, we do.
The source material challenges a deeply ingrained industry standard here regarding the 80% rule and the law of diminishing returns.
It's brave, really, because it tackles the coverage metric not as an engineering absolute, but as an economic trade-off.
Okay, so during the live orchestration session, they actually audited the CodeCov metrics across their ecosystem. And out of the 16 primary repositories, 3 fell significantly below an 80% coverage threshold. You had DiGraphinex sitting at 72%, NetListX was at 78%, and Spherin was sitting all the way down at 53%.
Yeah, 53 is low.
Now, wait a minute. As someone who intuitively loves to see a perfect score and all green checks on a dashboard, the immediate instinct is to halt the releases and just write tests until those hit 100%.
Naturally.
If the pipeline is that fast now, why wouldn't we demand every single line of code be verified?
This raises an important question about the behavioral psychology of development.
Okay.
The presentation argues that enforcing 100% test coverage actively damages the code base by creating perverse incentives.
Wait, really? Damaging it?
Yes, because when developers are mandated to satisfy a coverage tool, the goal shifts from verifying complex logic to simply executing every line of code at least once.
Oh, I see. Which leads to writing incredibly brittle test suites.
Exactly.
You start seeing tests for trivial boilerplate, like data classes or basic getters that contain literally zero logic.
Right, just to get the green check.
Or, even worse, you see developers heavily mocking the file system and the operating system just to force a highly specific, nearly impossible error path to execute so the coverage tool marks the line green.
Yes. And you end up with test suites that are so tightly coupled to the exact syntactic implementation of the code that the moment you attempt a healthy refactor,
Boom.
50 tests fail.
Mm.
The logic didn't break. The rigid, overmocked tests broke.
Right.
So the presentation advocates shifting from absolute coverage to strategic coverage.
Which means, instead of a blanket percentage, you target the areas with the highest impact and the highest risk. You aggressively test core algorithms. You target edge cases because unexpected inputs are always where state mutations fail.
Always.
You rigorously cover error paths to prevent silent failures in production. And you lock down the public API because that is the immutable contract you hold with your users.
Exactly. And the numbers attached to this strategy are highly pragmatic.
Yeah.
The 80% rule is treated as a healthy floor for most modules. 95% is considered the practical maximum you should ever attempt to reach. Because the effort required to move a repository from 95 to 100 yields severely diminishing returns.
Right.
It consumes time that really should be spent optimizing your architecture instead.
So bringing this all together, the overarching theme of this deep dive into Lucka 3.6's presentation is pretty profound.
It really is.
Managing multiple repositories efficiently, really scaling up your architecture, isn't just a matter of learning faster CLI commands. It requires a fundamental shift in how you view your infrastructure. The ultimate takeaway here is that your continuous integration system is not a gate you have to squeeze your code through. It is an active debugging partner.
It's your co-pilot. If you apply these principles, keeping your graph history mathematically clean with boundary merges, leveraging a multi-dimensional CI matrix to instantly isolate environmental variables, and deploying strategic test coverage rather than chasing a hollow 100% score, you are ultimately protecting your most critical resource as an engineer. You are protecting your time.
Yes. You stop playing whack-a-mole with local bugs and start operating like an architect overseeing a massive system.
Exactly. And, I want to leave you with a final lingering thought inspired by a really crucial limitation in the coverage tools we just discussed.
Ooh, okay.
Code coverage metrics only measure what lines of code were executed during a test run. They do not measure what was actually verified.
Oh, wow. So the coverage tool just knows the interpreter touched the line.
Precisely. A test script can execute 500 lines of highly complex asynchronous logic. But if that test script does not contain strict assert statements validating the final state of the data,
the coverage tool will still report all 500 lines as perfectly covered.
Exactly. So I ask you to ponder your own test suites for a moment. Think about that multi-repo ecosystem you are building right now. How many of your perfectly passing, beautifully covered tests are silently executing broken logic without actually asserting anything of value? It's like a building inspector walking through every single room of a skyscraper with a clipboard, checking off that the rooms exist, but never once turning on a faucet to check the plumbing.
That is terrifying. You could have an entirely green dashboard masking a fundamentally broken system. Go check your assertions.